Welcome back to our ongoing discussion on surface chemistry. This is our third meeting and we will first continue with what we discussed last time. In the last class, we discussed about physisorption and chemisorption. And we also talked about the differences between what physisorption is and chemisorption is. So, here is a small table which captures the differences between physisorption and chemisorption. So, I have listed out on this thing the differences between physisorption and chemisorption. Physisorption we say is non-selective. So, if you have a surface, then no matter what the molecule on top of it is going to get adsorbed. Chemisorption on the other hand is a selective process, which means that some gases or liquids will not adsorb on some adsorbent. Okay. Then the process which determines whether and the strength of the physisorbed species will be determined by the intermolecular forces that exist between the adsorbed molecules, whereas in the case of chemisorption there is a chemical bond formation between the adsorbent and the adsorbate, as a result of which this is what makes the process selective. Not all adsorbents can adsorb species. The third difference, and this is a significant difference, is that the activation energy for physisorption is 0, which means that it is almost has no barrier to physisorption, and in the case of chemisorption there is an activation barrier, but it might be small. And a very significant difference is that the enthalpy of adsorption, because of physisorbed species being involved through intermolecular forces, the enthalpy of adsorption is quite small, that is, it is only about 10 to 40 kilojoules per mole. And we also said that these numbers may differ based on the kind of book that you look at. The enthalpy of adsorption for chemisorption would be 100 to 400 kilojoules per mole. And because the adsorbed species forms a chemical bond with the surface, in the case of chemisorption you can only have monolayer adsorption. So, these are some of the significant differences or a comparison of how physisorption differs from chemisorption. This is important enough for you to sort of make a note of. And we will move on and we will look now at how these intermolecular forces determines the extent of physisorption. I have taken a particular example of the adsorption of various gases, and I am looking at the adsorption of activated charcoal, 1 gram of it at 15 degrees Celsius. And here are various gases. It is not important for you to know any of these numbers, either this or this, but it will give you a trend. And this trend is something that you have seen when you looked at states of matter. For example, what is the boiling point, trend in the boiling point that one observes, and how you have tried to correlate the trends in the boiling point with the intermolecular forces that exist in the molecules. And this is a similar kind of thing. Here are various gases, and I have listed some of them. There is phosgene here, and to 1 gram of charcoal at this temperature, 440 cc's of phosgene is adsorbed, and you go down this list. There is sulfur dioxide, ammonia, hydrogen sulfide, N2O, etc. And you see that in this list the extent of adsorption characterized by the volume at STP, you will see that this decreases as we go down here in this list. It starts off at 440 centimeter cube for phosgene and goes down to 5 centimeter cube for hydrogen. There is nitrogen, oxygen, etc., gases which are of great importance in the chemical industry. And for comparison, I have given here the boiling point in degrees Celsius and also the critical temperature in degrees Celsius. And you will see that there is a reverse trend. So, the boiling point of phosgene is minus 8 degrees Celsius and it goes down in the same order that is happening here. So, as the volume decreases here, you will see so does this the boiling point of the various gases. So, phosgene has the highest boiling point. It also has the highest critical temperature, and we also know from our studies of the states of matter that the critical temperature is a measure of how easy or difficult it is to liquefy a gas, and liquefaction of gases arises as a result of intermolecular forces. If the intermolecular force is small, then liquefaction is difficult, and this is exactly what we see here. Here we see that hydrogen has a very low critical temperature. So, this is difficult to liquefy. And this is easy to liquefy. And what we are saying is ease or difficulty of liquefaction is directly related to the extent of intermolecular forces that exist. If two molecules tend to attract a lot, then it will easily form a liquid. Whereas, if two molecules essentially behave ideally, then there is no reason for them to come close, and as a result liquefaction becomes difficult. And that is exactly the correlation that we see in the adsorption too. Those that are difficult to adsorb are difficult to liquefy, and those that are easy to adsorb are easy to liquefy, because they have more intermolecular forces. So, intermolecular force is high here and low here, and if you have more intermolecular forces, they adsorb easily, also have a higher critical temperature, and so on. Okay. So, this is some of the things that we discussed in the last class, and we also in the last class, which I have to reiterate, looked at what is the difference in the potential energy profile when we have physisorption as opposed to chemisorption. I have drawn here a potential energy curve which is exactly a reproduction of what we had in the last class, except that it is less cluttered, and I am looking at the physisorption of oxygen to a surface here. So, this is the metal surface you imagine, and oxygen is coming from here. This point here, the energy 0 corresponds to diatomic oxygen molecule, and the molecule comes to this distance at the, so it is coming, the oxygen molecule is coming towards the, here is the surface, and an oxygen molecule is coming from here along this. At large distances, essentially there is no interaction between the surface and the diatomic molecule, its energy is 0. And as the molecule comes closer and closer, it starts to feel an attractive force. Because of this intermolecular attraction between the surface, which is made up of, let us say, metal atoms, and oxygen, there will be an attractive interaction, and this attractive interaction leads to a decrease in energy, and this point here corresponds to when this diatomic molecule is attached to the surface like this. This is your diatomic oxygen, one oxygen atom here, one oxygen atom here, and this is your surface, and it has attached itself to this. And the distance between this point here and this point here, where there is a minimum, corresponds to the sum of the van der Waals radii of the metal and dioxygen. So, this corresponds to the sum of the van der Waals radii approximately, and this corresponds to the enthalpy of physisorption. And what we are saying is this enthalpy of physisorption is approximately 10 to 40 kilojoules per mole. So, this is a small well, and if you push this even further in, what happens is often this diatomic oxygen molecule, after it goes over this barrier, will drop down, and now you look at this picture. Now, I have a picture where the surface has two oxygen atoms attached to the surface. So, the oxygen molecule has dissociated into two atoms and bound to the surface. So, they are now bound to the surface like this, and I have two different oxygen atoms. So, this is a very, very critical thing, and the position of this barrier will depend upon where these two curves cross. If you have a crossing of these two curves below the 0, then there is 0 or less than 0 activation energy to go from the physisorbed state to the chemisorbed state. On the other hand, as is represented here, if the curve crossing happens above 0, then this is the energy of activation to go from the physisorbed state to the chemisorbed state. And look what you have achieved. You have taken a diatomic oxygen molecule, and when you pushed it further and when it got chemisorbed, as it is called dissociatively adsorbed, what you have got is essentially achieved this. This point here corresponds to dissociated oxygen. If you had to dissociate oxygen molecules in the gas phase, you have to essentially break the OO bond, and this OO bond dissociation energy is typically very high. So, if you take any diatomic molecule, if you take O2 or you take H2 or you take N2, any of these will do a similar kind of thing. So, this difference in energy is much higher than what you required to go over this hump, and you have achieved this breaking of the two atoms in the diatomic by going through a much lower barrier than you would have needed if you had to break the OO bond in the gas phase. And moreover, this energy corresponds to the enthalpy of chemisorption, and this corresponds to an oxygen atom that is chemically attached to the metal surface. So, this energy is significantly higher, and it could be anywhere from 100 to 400 kilojoules per mole, a typical bond energy involving any two atoms. So, we have an enthalpy of adsorption when you have a chemisorbed species much higher than what you would have in the physisorbed state. So, you can see from this potential energy picture the difference between chemisorption and physisorption. And we will move on now and look at, to close this discussion on adsorption, we will quickly look at what are the uses of adsorption. We have in the past discussed in passing some of these uses. The first thing that we talked about is gas masks. When you live in a polluted city like in Delhi, you will see lot of people, especially when the pollution levels are very high, wearing masks, and these gas masks that are used are based on the principle of adsorption. So, it has these gas masks have some material which have high surface area, and the particulate matter and other gases that are there in the atmosphere are adsorbed on these gas masks. So, for use of these gas masks, the better ones, you have to change the filter that is there in the gas mask. So, that is one use that you can think of for adsorption. We already said that if you want to study surfaces, you can easily see that you need very high vacuum, as it is called ultra high vacuum, if you have to study surfaces. And to create high vacuum, one of the ways to do it is you have to have an adsorbent in the chamber that you want to evacuate. After you get the vacuum down to a very low level, you put an adsorbent in the chamber that you wish to create a vacuum in, and the vacuum will drop more, because the gas that is there gets adsorbed on the adsorbent. So, that is another use. And I already talked to you about electronic packaging for mobiles and cameras especially, that have a small packet which is a desiccant. A desiccant is a material of high surface area like silica, for example, which adsorbs all the moisture that is there in the packaging. This keeps the electronics in good condition. Humidity causes problems to optics. So, this is a way of controlling the humidity by using the adsorption phenomena. If you go to a sugarcane industry where sugar is produced, one of the things that is used is activated charcoal to remove coloring matter. You will see sugar that we get in the market is typically white, whereas if you looked at the raw material that is used for the sugar production, that actually looks brown colored. And one of the uses for this adsorption is to remove the coloring matter that exists in many of these food materials that we finally eat. And this is something that we have not discussed, but you must have encountered this in your discussion of extraction of metals from their ores, that is froth flotation. And inert gas separation, as you can imagine, because of the chemisorption phenomenon being selective, you can remove one gas over the other based on their adsorption properties. So, you will have a chemisorption phenomenon where one gas will adsorb onto a material, whereas the other gas will not, and you can use this to separate out two gases. The next two uses of adsorption that we discuss is closely related to chemistry and its research these days. The first thing is chromatography, and this is something that you might have done an experiment with or an activity in your school. This is something that is called paper chromatography. You might have, this might have been done in a biology class, it is possible that you did it in a chemistry class. You take a leaf or leaves and you crush it and you extract out the coloring material of the leaf into water, and you take some amount of the extract that you get from the leaf and you put it onto a paper. You make a few drops on the paper and you suspend the piece of paper into water, and as time goes, due to capillary action, the water will rise along the paper. So, you suspend it vertically, and because of capillary action, the water will rise along the paper, and as the water rises, it will carry your leaf extract along with the paper. And the leaf extract has a lot of compounds. It has compounds of varying types, and so when this moves up along the paper, the different materials get adsorbed on the paper differently, and because they are absorbed differently, they will move up the paper differently. So, as the water level moves up along the paper, you will get a separation in the compounds that exist in the leaf extract. This is something that is very, very useful for chemists, because any reaction that a chemist carries out is going to lead to not only the product that you want and also to products that you do not want, and also to reactants that are not completely reacted. So, any reaction mixture at the end of the reaction contains useful things, not so useful products, as well as reactants. But finally, I need the useful product, and I have to separate out the harmful ones, the not so useful products, and the reactants from the reaction mixture. So, all chemists who are doing research on a day-to-day basis pretty much use chromatography in their lives. A similar thing that analytical chemists do, although it is becoming less and less popular these days, is to use indicators. Again, you might have done titration experiments. You have an acid base titration, for example, where you use phenolphthalein as an indicator. That indicator works on an acid base principle. The acid form has one color, the base form has one color, and when equivalence is reached, it undergoes a color change because the phenolphthalein goes from one color to another color. That is a color based indicator. And in these adsorption indicators, what we use is we have an indicator which gets adsorbed on some species, and that is used as an indicator. Eosine is a good example of an adsorption indicator. And one final thing which leads up into the next topic that we will discuss is catalysis. So, this is the thing that we will focus our attention on in the next little bit of our discussion, and that is catalysis. You have just probably gone through a discussion on chemical kinetics in an earlier unit of your textbook. And in chemical kinetics, what we are interested in is the rate of the reaction. And no matter what reaction you study, you are interested, especially if you are in a chemical industry, to improve the reaction either in terms of the time it takes to complete, or as I said, you want to get one product and not another product. So, the rate at which a chemical reaction happens is something that is of great importance in chemical industry. And one way to change the rate of the reaction is through the use of catalysis. And catalysis has a long history. The word itself came about through a person named Berzelius in 1835, and I will read this out for you, as this is what Berzelius said. And Berzelius was looking at trying to systematize a number of the observations of people who came before him. Essentially, he was looking at the dehydrogenation of ethanol in the presence of acid, and he was trying to summarize their results, and this is what Berzelius says. Berzelius says, it is then proved that several simple or compound bodies, soluble and insoluble, have the property of exercising on other bodies an action very different from chemical affinity. And chemical affinity is a term that you are probably not aware of. This is a force that was imagined to exist which led to the formation of compounds. So, what he is saying here is that several simple or compound bodies, soluble and insoluble, have the property of exercising on other bodies an action very different from chemical affinity. And he goes on and says, by means of this action they produce in these bodies decomposition of their elements and different recombinations of these same elements to which they remain indifferent. The language is obviously something that we 200 years hence probably do not appreciate very well, but if you read carefully, that is exactly the way we understand catalysis now, more or less. and we will move on and look at what is now the definition of catalysis. So, this is now the accepted definition of catalysis, and it says in the IUPAC Gold Book, which defines most of these things, a catalyst is defined as a substance that increases the rate of a reaction without modifying the overall standard Gibbs energy change in the reaction. So, that is a catalyst that increases the rate of a reaction without modifying the overall standard Gibbs energy change, and the process that this affects is called catalysis. That is the accepted definition according to the IUPAC Gold Book. And if you look at something which is there in common language, the Oxford English Dictionary says a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. This is what the Oxford English Dictionary says, and this is more or less correct. And there is another colloquial definition of Oxford English Dictionary also, which I have included here, and it says a person or thing that precipitates an event. That is also catalysis in the normal speak between you and me. But what we would be interested in is the definition according to the IUPAC Gold Book. So, let us move on. Catalysis, as I already stressed to you, is of great importance in the chemical industry. It is also been rewarded in a number of Nobel Prizes, and from our calculation it appears that about 15% of the Nobel Prizes that have been awarded have been to catalysis in some form or the other. And here I have listed some of the big players who have got the Nobel Prizes in catalysis. It starts off with Wilhelm Ostwald in 1909 for fundamental work on catalysis, Paul Sabatier for olefin hydrogenation, which is something that we use to make dalda, Fritz Haber for the ammonia synthesis and still used very extensively to this day, Ziegler and Natta for their catalyst for olefin polymerization. So, polyethylene, for example, is created or synthesized or produced, mass produced using the catalyst that was developed by Ziegler and Natta. Knowles, Noyori and Sharpless more recently, almost 2 decades ago, for chirally catalyzed reactions. Yves Chauvin, Bob Grubbs and Richard Schrock for their catalysts for olefin metathesis, which is to take an olefin and break it. And in 2010, Heck, Negishi and Suzuki for carbon-carbon coupling reaction using palladium as a catalyst. As you can see that catalysis has been rewarded with a number of Nobel Prizes. But just as importantly, and I have stressed this more number of times than you can imagine, the final key reason for the importance of catalysis is because of its role in chemical industry. And here I have listed major products of the chemical industry and how they are pretty much all generated through catalysis. So, here is the reactant, crude oil that you get from extraction, and you make a product which is your hydrocarbon fuels using a cracking catalyst, which is platinum on silica and alumina. The production of sulfuric acid from sulfur dioxide and dioxygen, this is a very, very important process, by far the most important process, with vanadium as the catalyst. That is something that is used extensively. The next one is the one that we talked about, Fritz Haber's ammonia synthesis from nitrogen and hydrogen using iron as the catalyst. The production of methanol from carbon monoxide, and you can see that all these things involving products which are of very, very great importance in our everyday lives. They may be only a precursor of things that you and I see on a regular basis, but most of these things are generated in reactions which involve catalysts. So, the importance of catalysts are everywhere, and it is only appropriate that we look at this a little bit more carefully. Before we look at how it happens and what is the general principle of catalysis, let us just look at some of the kinds of materials which act as catalysts, and you can see in this list pretty much everything can act as a catalyst. Metals could be catalysts, metal oxides could be catalysts, metal sulfides could be catalysts, acids could be catalysts, and I have listed here what the type of material that we have got, what kind of reaction they catalyze, and what are the examples, prototypical examples of each of these. So, for dehydrogenation or for hydrogenation of the type that got Paul Sabatier the Nobel Prize for olefin hydrogenation involving metals here, semiconducting oxides of the type that are listed here could be used for any one of these 5 categories of reactions that you have got. Insulator oxides of the type that we have written out here, they could be used for dehydration and isomerization, and acids like phosphoric acid, sulfuric acid, and Lewis acids like silica and alumina could be used for polymerization, isomerization, cracking, and alkylation. So, you find that all kinds of materials, metals, oxides, metal sulfides, acids, and I have not listed here 2 very important classes of catalysts. One is zeolites and the other is enzymes, which also serves as catalysts. Enzymes, by the way, are naturally occurring catalysts that is there in our human body, for example. So, they catalyze a whole range of reactions. So, catalyst, as they say, is ubiquitous, it is there everywhere. So, it is only appropriate that we look at what happens in catalysis. And to keep going, one of the things that you will notice is that catalysts could be of any type, and here I have listed some of them. So, what we say here is catalysts could be in the same phase as the reactants. So, here I have just a variety. So, the catalyst is a liquid. So, the reaction itself, imagine that I have a reaction A plus B going to C. That is a generic reaction, imagine that I am looking at, and this could happen either in the solid phase or in the liquid phase or in the gas phase. Reaction could happen in the solid, liquid or gas phase. It is possible that you have, if you have done any reaction, for example, a titration experiment, the reaction is happening in the liquid phase, but there is no reason why reactions could not happen in the solid phase or in the gas phase. So, in principle, reactions could happen in the solid, liquid or gas phase, and the catalyst also could be either a solid or a liquid or a gas, and that is what we have listed here. So, if the catalyst and the reactant is in the same phase, then we call this homogeneous catalysis. So, what are we saying? What we are saying is, if the reactant and the catalyst is in the same phase, then it is homogeneous catalysis. And here I have given 4 different, and there might be other possibilities. The catalyst is in the liquid phase, the reactant is also in the liquid phase, it is homogeneous, and here is an example, ester hydrolysis. So, this is ethyl acetate hydrolyzed by water in the presence of either acid or base. That is one example. The catalyst could be in the gas phase and the reactants are also in the gas phase, and this is an example, the oxidation of sulfur dioxide by oxygen in the gas phase in the presence of nitric oxide, which is also in the gas phase. So, this is the catalyst here. Here is the catalyst, here is the catalyst that I have underlined. The liquid phase catalyst, where the reactant could be both liquid and solid, and that is the hydrolysis of cellulose. So, this is the acid is the catalyst, it is present in the liquid phase. Water, which causes the hydrolysis, is in the liquid phase, and cellulose, another reactant, is in the solid state. A solid catalyst reacting with a solid and a gas. Here is an example, potassium chlorate decomposition. This is a solid, this is the reactant, and this is the example that is quoted in your book on catalysis. The decomposition of potassium chlorate does not happen very easily, but the moment you add manganese dioxide, this explosively undergoes a reaction. So, this is a solid and this is a solid, and the reactant is in the solid phase and the catalyst in the solid phase. So, here we have examples of homogeneous catalysis, and the reason we are interested more in heterogeneous catalysis is because of its applications in industry. So, now we move on and we look at some examples of heterogeneous catalysts, where reactants and catalysts are in different phases, and this we call as heterogeneous catalysts. Catalyst in the liquid phase, reactant in the gas phase. The polymerization of ethylene, ethylene is the reactant, acid is the liquid phase, phosphoric acid. Here is an example, solid catalyst, liquid reactant, cyclohexene disproportionating. Cyclohexene is a liquid, palladium is a solid, is a catalyst. Its cyclohexene goes into benzene and cyclohexane, that is disproportionation for you. A solid catalyst with a gas phase reaction. Carbon monoxide is the reactant, zinc oxide is the catalyst, and a solid catalyst with reactant in both liquid and gas phase. The hydrogenation, which is in the gas phase. So, hydrogen is one reactant, gas phase hydrogen reacting with benzene, which is in the liquid phase in the presence of nickel as a catalyst, is an example of the last kind. So, I have now given you why we need to understand catalysis, and we have also discussed some examples of various kinds of homogeneous and heterogeneous catalysis. Now, what we need to do is to look at what all this means, and for this we will appeal to our knowledge from chemical kinetics. We already have seen, if you remember, recollect your discussion on chemical kinetics and something to do with the temperature dependence of rates. You plotted, if you looked, you plotted this both, whether it was in collision theory or temperature dependence of the rates, you plotted energy here and you plotted what is called the progress of the reaction. Or the reaction coordinate here. For any reaction, you plotted something which looked like this. So, whether it is E or H or G, it does not matter, some kind of energy along this axis and a very strange variable called the progress of reaction. It's especially bad because it is called a reaction coordinate. It is easy to confuse this with some Cartesian coordinate, but it is not a single coordinate, mind you, it is a strange coordinate, something which tells you that the reaction goes from the reactant side to the product side, the reaction coordinate. and you plotted this. So, here you have the reactants and here you have the products. This separation in energy is the delta H or the delta G or the delta E of whatever this reaction that you are looking at. So, in this case, as I have drawn it, this reaction is exothermic because the products are lower in energy than the reactants, and this is what is called the energy of activation for this reaction going from the reactant side to the product side. And this is what Arrhenius, we attribute this to Arrhenius, who wrote out this equation that the rate constant for this reaction is given by A e to the minus E A over R T. This is something that you must have come across in your discussion of chemical kinetics, and we will use this extensively in our discussion going forward. Okay. What does the Arrhenius theory says? This quantity here, the pre-exponential factor as it is called, is a measure of the number of collisions, is approximately a measure of the number of collisions that we have between two species that are undergoing the reaction. So, and you can compute the number of collisions by looking at kinetic theory of gases or something simple like that. So, this we know we have a measure of, and this quantity here essentially gives you the fraction of molecules, fraction of collisions with enough energy. So, what does this say? This tells you that you could have collision between molecules, lots of them. If I have two cars that come and collide, so the reactants look like cars, they come and collide. If the two molecules or cars coming together coming slowly, they will collide, will not have that much momentum, and so then they will have a collision. There are others which are coming fast and they collide. So, these have different energies because the kinetic energy of the molecules are different, and what we are saying is some molecules have the energy to overcome that barrier, and this is completely governed by kinetic theory. So, the fraction of molecules which have this barrier will go from the reactant side to the product side, and this is critical to understand, because if you want to understand catalysis, this is the key. So, I have, imagine a reaction between A and B, or let us imagine that H2 plus O2 giving you half O2 giving you H2O. So, the reactant here, to give you a concrete example, is H2 plus half H2, and this is H2O. And if I looked at this reaction H2O, the delta G is very largely negative, something like minus 250 or so, approximately minus 250 kilojoules per mole. That is what we have. But you can keep H2 and O2 mixed in a container without a reaction ever happening between these two. You keep these two mixed, although the Gibbs energy is negative, you can stay there forever. But the moment you add some metal like iron filings or some other metal, these two react explosively to give you water. So, this is a very, very subtle thing. So, the Gibbs energy is negative. So, it is thermodynamically feasible reaction, but the reaction does not happen at all until I had some iron filings or some other metal. So, what is it that the catalyst, in this case iron filings or some metal that is added, what does it do to make this reaction go from here to here? And the way it does this, the catalyst, what it does is to give an alternative path to go from the reactants to the products. So, here is one well, this well. So, this is a catalyzed reaction. This picture looks a little bit different from the picture that is there in the book, but I will explain that in a moment. So, H2 and O2 in the presence of a catalyst will get adsorbed on the surface of the catalyst, as a result of which the energy goes down. That is this point here. So, this point corresponds to hydrogen and oxygen bound to the catalyst surface, which is not there in the absence of a catalyst. So, this is this dip. This hump corresponds to the activation barrier for the adsorption process, and look at this. This barrier is much smaller than this barrier, and that is the key. So, you get into this. Now, I have an activation barrier to go from this. A reaction happens. So, I have hydrogen which is adsorbed to the surface, oxygen that is adsorbed to the surface, and this point. They undergo a reaction, and now I get water. This point here corresponds to water which is adsorbed to the surface. So, that is why this profile looks a little bit different from the one that is there in the book. The one that is there in the book just shows you like this. So, this is adsorbed hydrogen and oxygen, this is adsorbed water, and then it goes over this hill and gives you water. So, note critically, and this is what the definition of the IUPAC has, the Gibbs energy change in going from here to here is exactly the same for the blue profile as it is for the green profile. So, for the catalyzed reaction as well as for the uncatalyzed reaction, the Gibbs energy change is the same, which means that the equilibrium constant product over reactance is the same no matter whether you put a catalyst or you do not have a catalyst, which means that the forward rate is affected exactly the same way as the reverse rate. So, the equilibrium constant is completely unaffected. That is why it says that it increases the rate of the reaction without changing the Gibbs energy change of the reaction. The Gibbs energy change here is unaffected by the presence of a catalyst, whereas the rate of the reaction is. But there is something that you have to be worried about in this picture. This picture connects reactants to products. This does not mean that the catalyzed reaction goes through the same path as the uncatalyzed reaction. And this is like saying, I will try and give you an analogy. Imagine that I have to go from point A to point B. There is a straight path which goes here, and imagine that I have at this point a red light here. That is my red light, and this red light, because of the traffic, is hugely clogged. So, imagine that I have a huge traffic jam here. So, molecules which come from here, cars that come from here, because of this traffic light which takes long to change, and because of the numbers of things here, getting to B is difficult as a result of this traffic light. The smart drivers avoid this traffic light and take another path which does not have any lights. So, now if you are a molecule, rather than go through this straight path, you run from A to B, but it looks like the distance you are traveling is more, but because you have short circuited this red light here, you reach to B faster, and that is exactly what is happening here. Here you have an uncatalyzed reaction, and this red light corresponds to the huge energy of activation that you have got for the uncatalyzed reaction, whereas here, because you have no red light, this happens to be the catalyzed reaction. So, that is the analogy between something that you encounter on a regular basis. Do not push the analogy too far, but it gives you a way of understanding how a catalytic reaction works. Okay. The other thing that we look at is if you plotted, what we are saying is the EA of uncatalyzed reaction is much greater than the EA of the catalyzed reaction. So, if you plotted ln k versus 1 over T, we know from our discussion in chemical kinetics that it looks like this. So, imagine this is the uncatalyzed reaction. And imagine I am looking at a reaction where I am using a heterogeneous catalyst. This point here corresponds to ln A, which we said is a representation of the number of collisions. So, we have this for the uncatalyzed reaction, and for the catalyzed reaction we are saying that the energy is smaller. So, if you looked at this, this happens to go like this, and this is the catalyzed reaction. Why do I represent this as smaller? Because now the two species are adsorbed on the surface, and once they are adsorbed on the surface, the number of collisions that you have is going to be lower than if you have in the gas phase. Imagine that you have lot of molecules in the gas phase, some of which gets adsorbed, and once you are adsorbed, the number of collisions that you have is going to be significantly smaller than the number of collisions here. So, there are two counteracting things. The heterogeneously catalyzed reaction has a smaller number of collisions, but it also has a smaller EA. So, this EA cat, and this is again a little bit counterintuitive. The slope is lower for the catalyzed reaction, the slope is higher for the uncatalyzed reaction, right. ln k is equal to ln A minus EA over RT, and the catalyzed reaction has a larger slope which is here. So, the number of collisions is fewer in the catalyzed reaction, but EA is also smaller. So, if you have to have the catalyzed reaction actually work faster than the uncatalyzed reaction, you have to compensate for the decrease in the number of collisions by seeing a larger decrease in the EA. And here are two examples of, I am giving you some examples of where what kind of EAs that we are seeing here. So, here are some examples. Here is the reaction of hydrogen iodide to give you H2 and I2. In the absence of a catalyst, the activation energy is 185 kilojoules per mole. In the presence of gold, it has gone down by about 80 kilojoules per mole, and for platinum it is even further down. So, the number of collisions that you had is compensated for by this change in the activation energy. And here are two more examples. In both cases, we will find that when you have no catalyst, the energy of activation is higher than when you have a catalyst. With that, we will close for the day. Thank you.